97% of Docker containers can't reproduce the exact same build 6 months later, and developers have no idea.
Wait, are you saying our Docker builds aren't actually reproducible? So we're comparing Docker's reusability problem with Nix's solution and this new Flux tool that makes it accessible.
By minute 4, you'll know exactly why your builds are breaking and how to fix them. Let's get into it.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're diving into Docker versus Nix, the quest for true reproducibility.
Stick around to the end for today's headlines. Let's dive right in.
So let's talk about reproducibility. It's a word we throw around constantly in platform engineering, especially when we talk about containers. We've all accepted Docker as this brilliant invention that lets us package an application and its dependencies, and we treat the resulting image as this immutable, reproducible artifact.
Right. That's the whole point, isn't it? It solves the "it works on my machine" problem. I run Docker build, I get an image, I push it to a registry, you pull it, you run it, and you get the exact same environment I had. Reproducible. End of story.
That's the promise, but the reality is much more porous. What most of us get from a standard Docker build isn't true reproducibility, it's reusability. You can reuse the image I built, yes, but if you try to reproduce that exact image from the same Dockerfile, even just a day later, you'll almost certainly fail.
Hang on. How? The Dockerfile is declarative. It's a recipe. If I run the same recipe twice, I should get the same cake.
But what if one of your ingredients is whatever flour is on sale today? Most Docker files have a line in them like run apt-get update and apt-get install-y my package, or yum upgrade. That command is non-deterministic. The packages it pulls depend on the state of the upstream repository at the exact moment you run the build. The LIC you get today might be different from the one you got yesterday. It might have a new security patch, which is good, or it might have a new subtle bug, which is very, very bad.
Okay, I see what you're getting at. It's a form of configuration drift, but it's happening at build time, not runtime. So even if my application code is pinned with a git SHA, its underlying dependencies are shifting under my feet. What are the real-world consequences of that? Is it just theoretical?
It's not theoretical at all. Think about performance benchmarking for complex I/O-intensive applications like ScyllaDB or Cassandra. You run a benchmark in January on an image you built that day. You make some performance tweaks to your application, and you run another benchmark in March on a newly built image. The results look great, but how much of that performance gain was your code, and how much was due to a background upgrade of the kernel's I/O scheduler dependencies pulled in by apt-get? You can't be sure. Your comparison isn't apples to apples anymore.
And the security implications are even worse. My security scanner clears an image on Monday. On Tuesday, a new vulnerability is discovered in a transitive dependency, say libSSL. On Wednesday, a developer rebuilds the image for a minor bug fix. The build process innocently pulls in that newly vulnerable libSSL version because the Dockerfile just says install OpenSSL. The new image gets deployed, and suddenly we're exposed, even though our application code hasn't changed, and the original image was clean.
Precisely. You end up with these hidden inconsistencies. The industry expert Michael Stanke put it perfectly. Reproducing that image is actually pretty difficult to do. You can try to pin every single package version in your apt or yum command, but that's incredibly brittle. You have to pin the entire dependency tree, not just the leaf node. It's a nightmare to maintain. We've been using a tool that gives us a fantastic illusion of consistency, but it has fundamental gaps.
So if Docker isn't the answer for true bit-for-bit reproducibility, what is? We can't just go back to deploying on bare metal.
We need a different model entirely, one that doesn't just manage packages, but treats the entire dependency graph like a mathematical equation, an approach where the inputs are guaranteed to produce the exact same output every single time, forever.
Coming up, we'll dig into exactly how a tool with roots in academia, Nix, applies principles from functional programming to achieve this near-perfect level of determinism.
The core problem with traditional package managers inside a Dockerfile is that they are stateful and time-dependent. They reach out to the internet and ask, "What's the latest version of X?" Nix flips this on its head. It's built on the principles of functional programming. At its heart, it treats a software package build as a pure function.
A pure function, like in programming. Given the same inputs, you always get the same output with no side effects. How does that translate to package management? The inputs are source code, I get that, but what else?
The inputs are everything. The source code, of course, but also the exact versions of all dependencies, the compiler, the build tools, the libraries, everything, all the way down to glib. The build script itself, the platform it's being built for. Nix takes all of these inputs, hashes them, and uses that hash to create a unique, immutable output path in a special directory called the /nix store.
Okay, hold on. A hash of everything? So if I change a single compiler flag or upgrade from GCC 11.2 to GCC 11.3, I get a completely new hash and a new package in this /nix store?
Exactly. That's the magic. The output path might look something like /nix store /s16z myapp 1.0. That long string of characters is derived from the hash of all its inputs. If you change anything, a single line of code, a dependency version, the hash changes and you get a new separate directory /nix store /f43b myapp 1.0. The old version is still there, untouched.
Sounds like it would create a massive mess on my file system. If every tiny change creates a whole new copy of a package, my disk is going to fill up in about 5 minutes. And what does my application see? How does it find its dependencies if they're all in these weirdly named hash directories?
It's surprisingly efficient. Nix is smart about sharing. If two packages depend on the exact same version of OpenSSL, they will both point to the exact same path in the /nix store. There's only one copy. The mess is actually a brilliantly organized, content-addressed storage system, and your application doesn't have to worry about finding things. When you build an environment with Nix, it constructs the necessary path and other environment variables with pointers to the correct hash paths in the store. Everything is explicit.
So, no more dependency hell. I could have a project that needs Python 3.8 and OpenSSL 1.1, and another project on the same machine that needs Python 3.11 and OpenSSL 3.0, and they can coexist peacefully because they point to different isolated paths in the Nix store.
You've got it. No more fighting with virtual env or RVM or NVM. Your system can have dozens of versions of the same library installed, and they will never conflict. This is what enables true reproducibility. If you and I share a Nix file called a derivation that defines an application and we both run Nix build on it, we are mathematically guaranteed to get a bit-for-bit identical binary output because all the inputs are explicitly defined and hashed. There's no room for non-determinism.
Okay, the power is undeniable, but let's talk about the elephant in the room, the developer experience. I've heard horror stories about the Nix learning curve. The Nix language itself is its own functional language, right? It's not as simple as writing a few run commands in a Docker file. Is the technical purity worth the cognitive overhead for the average team?
That has historically been the biggest barrier to adoption, and it's a valid concern. For years, Nix was seen as this incredibly powerful tool that was just too difficult for most developers to pick up. But that landscape is changing rapidly. The introduction of a feature called Nix Flakes has been a game changer. Flakes provide a standardized structure for Nix projects, and crucially, a lock file, a flake.lock, that pins the exact versions of all your inputs, including other Nix repositories. It's like package.lock.json for your entire operating system.
A lock file for the whole dependency tree?
That's compelling.
And it's not just a community effort anymore. A whole ecosystem of companies is building up around making Nix more accessible. Companies like Phlox, founded by a former Docker exec, and Determinate Systems are creating tools and services to smooth out that learning curve and bring Nix to the enterprise. They're trying to solve the usability problem because they recognize that the underlying technology is too important to ignore, especially in today's security climate. This level of control is incredible, but how do we actually use it to defend ourselves? Stick around and we'll break down how reproducible builds are becoming a critical defense against software supply chain attacks and what practical steps you can take to get started. Let's bring this back to the most urgent reason why platform engineers should care about this: software supply chain security. We've seen major attacks like SolarWinds and CodeCov where build systems were compromised to inject malicious code. How do you even detect that?
It's tough. You'd have to audit the binaries, which is incredibly difficult. You're mostly relying on post-breach detection.
But what if you didn't have to? With a truly reproducible build system like Nix, you can establish a chain of trust. Your CI system builds your application from a specific Git commit using a locked Nix flake. It produces a binary and calculates its cryptographic hash. That hash is now your proof of authenticity. When you deploy that binary, you can rerun the build process independently and verify that the hash of the new output matches the original hash from your trusted CI pipeline.
So if a downstream system or even a malicious actor inside your company tries to tamper with the binary before deployment, the hash verification will fail. You're not just trusting that the binary is the one from CI, you can mathematically prove it.
Exactly. It turns trust me into verify me. This is a paradigm shift for auditing and compliance. Now, the big question is, how do you get started? As you said, you can't just tell your entire engineering organization to abandon Docker and learn the Nix language overnight.
Right. I'm sold on the why, but I need the how. What's the first non-disruptive step for a team that's 100% invested in Docker and Kubernetes?
The path is incremental. You don't have to go all in on Nix OS. First, start with developer environments. This is the lowest hanging fruit. Instead of a messy README telling developers to install 15 different tools with brew or apt, you create a single shell.nix or flake.nix file in your project repo. When a developer enters that directory, tools like direnv can automatically activate a shell with the exact versions of the compiler, linter, and libraries needed for that project. It's a massive productivity win and introduces the team to Nix concepts in a low-stakes way.
So you're isolating developer tooling first. What's next? Do we have to abandon Docker images?
Not at all. The next step is to use Nix to build your Docker images. This is the Docker with Nix approach. Instead of a Dockerfile with run apt-get install, your Dockerfile becomes incredibly simple. It might just be from scratch and copy/result/. The heavy lifting is done by Nix. You use Nix to build your application and all its dependencies into a self-contained directory tree. Then you use Nix's built-in dockertools.buildImage function to package that result into a minimal OCI-compliant image.
So I get the bit-for-bit reproducible content from Nix, but the final artifact is a standard Docker image that works with all my existing tooling, Kubernetes, my container registry, everything. I'm just replacing the non-deterministic build part.
Precisely. You get the best of both worlds, the reproducibility of Nix for the build and the ubiquity of the OCI standard for the runtime. These Nix build images are also often smaller and more secure because they contain only the exact dependencies needed, not a whole base OS with tools like Bash or curl that could increase the attack surface.
So the future isn't necessarily Nix replaces Docker. It's more about using the right tool for the job. Nix for the build layer and OCI containers for the distribution and runtime layer.
I think that's the most pragmatic view. The core takeaway for any platform team is to understand the spectrum of reproducibility. Standard Docker builds are on one end, good but imperfect. Nix is on the other end, mathematically pure, but with a learning curve. Your job is to decide where on that spectrum your different services need to be.
A marketing website? A standard Docker build is probably fine. Your core authentication service or financial transaction processor, the security and auditing guarantees of a reproducible build with Nix become incredibly compelling.
It feels like the industry is finally getting serious about proving the integrity of what we build, not just shipping it.
It's a sign of maturation. For a decade, we were focused on speed and agility, move fast and break things. Now, we're entering an era where speed must be paired with security and verifiability. The quest for true reproducibility isn't just an academic exercise, it's the foundation for building trustworthy software at scale. Sound of a subtle modern audio logo fades in and then out. Before we wrap up, let's catch up on this week's infrastructure news. Platform engineers need to pay attention to what's happening in calendar week 6. Igor's Labs LeakWatch 2026 is reporting multiple security incidents, including breaches at Coupang and Substack.
These aren't small players either. What kind of data was compromised?
The report highlights various data leaks and IT breaches across the board. It's a reminder that even major platforms aren't immune to security incidents, which is why platform teams need robust security practices baked into their infrastructure.
Speaking of infrastructure, have you seen the buzz on Reddit about QN3 Coder Next? Someone's calling it the first truly usable coding model under 60 gigabytes.
Yes, the author on r/local llama says it's a game changer for local development. They're praising its speed, quality, and how it handles context size compared to other models in that weight class.
Under 60 gigabytes makes it actually deployable on developer workstations. That could really change how platform teams integrate AI coding assistants into their workflows.
Now, here's something that'll make CFOs sweat. MLQ.ai reports that big tech companies are planning to spend between $650 and $700 billion on AI infrastructure by 2026.
That's Alphabet, Amazon, Meta, and Microsoft combined, right? That's an astronomical amount of capital expenditure.
It is, and it's completely reshaping their cash flow dynamics. Platform engineers should take note. This level of investment signals where the industry is heading in terms of infrastructure requirements and capabilities.
And Goldman Sachs is already putting that AI to work. They've partnered with Anthropic to deploy Claude AI for accounting and compliance automation.
According to MLQ.ai, they co-developed these AI agents over 6 months, and they're seeing significant improvements in client services. It's not just chatbots anymore. We're talking about AI handling complex financial compliance tasks.
That's a perfect example of how platform engineering is evolving beyond just keeping services running to actively transforming business operations with AI infrastructure.
That wraps up today's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
And check out platformengineeringplaybook.com for more resources and guides. Until next time.